In this video, we're going to go through spectroscopy and the electromagnetic radiation spectrum. So here is the electromagnetic radiation spectrum. And you see visible light right here is only a small fraction of the spectrum. I also want you to notice that red has a longer wavelength versus violet, which has a shorter wavelength. And we use the symbol lambda to represent wavelength. All right, so spectroscopy is a method of analysis which is based upon the absorbance of electromagnetic radiation by matter. We use spectroscopy to acquire data pertaining to the structure of a molecule or the concentration of a species. So think about all of the planets and stars that are out in the galaxy, the universe. We're able to analyze the light emitted by these different stars to determine the composition of distant planets, distant suns, and without having ever been there. So here's an example of light hitting an object. So our incident light, or IO, is the intensity of the radiation striking the example. I sub t is the intensity of the radiation exiting the example. So this is in, this is out. And then I sub a is the intensity of the radiation absorbed by the sample. So the incident light is not, in most cases, going to be the same as our light that is exiting a sample. So usually light will be absorbed by a sample and you're going to have a different color that is reflected by that sample. All right, so we have two methods for spectroscopic analysis. We have ultraviolet or visual spectroscopy, and this method examines transitions in electronic energy levels. We use it to probe the electronic structure of certain compounds. And we also use it to determine the concentrations of solutions that contain certain compounds. So we'll shine a light through a sample and we'll look at the light that exits on the other side. The other type of spectroscopy that we have is infrared spectroscopy. And this examines transitions in molecular vibrations. We use this to detect different types of bonds and to identify molecules. So ultraviolet or visual spectroscopy, as I mentioned, we use an absorbent spectrophotometer to measure the absorbance of a sample at wavelengths between about 200 nanometers and 800 nanometers. So I just want to note that that is visual. That's what we can see. That's what our eyes can detect. The peaks represent wavelengths, represented by the letter lambda, that correspond to the energy, which is E, associated with possible electronic transitions within the molecule. So we have two main formulas that we're going to use. We're going to have V, which is our frequency, equals the speed of light over lambda, and then we have E is equal to H times V. H is Planck's constant. And something I want to point out, in both formulas, we have frequency. So I can actually substitute in my speed of light here over my wavelength for my V here, and I get a single equation over here. So it's not actually three separate equations. I'm just doing a little bit of substitution here in my energy equation so that I can represent my frequency as speed of light over wavelength instead of frequency. So if I have a wavelength, I can solve for energy using this equation right here. All right, so infrared spectroscopy, a couple things you need to know. All covalent bonds in molecules are vibrating, and we'll look at a figure here in a second. Bond length is the average distance between the molecules, right? So you've got molecules that are bonded. So we're talking about this distance between those molecules right here. Covalent bonds have a vibrational frequency that is in the infrared region of the electromagnetic spectrum. So if we go back up and look, infrared is just outside of visible light. So it's a longer wavelength than red. Infrared radiation of exactly the same frequency will be absorbed by the molecule. So that is a key point right there. So infrared radiation of exactly the same frequency will be absorbed by the molecule. Vibrational frequencies depend on the mass of the atoms and the strength of the bonds. So if you have bigger atoms, obviously they're not going to be able to vibrate as easily because that's more mass that you need to move. And likewise, if you have stronger bonds, that's going to lead in less vibration as well because they're being secured with more force. And we know that frequency is related to wavelength. So actually, that is not the right equation. Our equation is up here. So it is an inverse relationship. So if you have a larger frequency, you are going to have a smaller wavelength. So if we look at two waves, right, we've got wave A and we have wave B. So wave A is a much longer wavelength. There's more distance between the waves, whereas wave B, it's a smaller wavelength. There's less distance between the waves. So wave A is going to happen more frequently, whereas wave B is going to happen less frequently. So you'll have one complete cycle a lot quicker in B than you would in A. Okay, so here's what I'm talking about with vibrational frequency. So you've got molecules that are going to be basically moving towards and away from each other. So they're going to be attracted and repelled by those bonds. Another type of spectroscopy that you need to be aware of is microwave spectroscopy. Microwaves cause polar molecules to rotate. So remember, on a polar molecule, you've got that dipole, right? So you've got a positive and a negative end, and it's going to cause those molecules to spin. It's going to cause them to rotate. Each type of polar molecule has a specific rotational frequency that they can exhibit. These peaks in microwave spectra below correlate with the different rotational frequencies for a specific polar molecule. Data from microwave spectra can be used to calculate the bond length of diatomic meaning you have like hydrogen, not hydrogen, diatomic. Diatomic is where you're going to have just two elements there. Polar molecules determine the shape of polar molecules. So an example of a diatomic polar molecule would be like HCl. So it's made up of two different elements. So something that is nonpolar would be like hydrogen. Hydrogen here is made up of the same element, so this would be nonpolar, whereas this one here would be polar.